Hey guys, it's Joe East here. Today we're going to talk about battery systems. In particular, we're going to show you how to do parallel and series stack-ups. So we're going to take these little bitty cells and we're going to start adding a bunch of stuff around these cells and add these cells together and pack them into parallel systems or series systems. I'm going to show you guys how to think through setting these systems up here. So the audience is designers, if you're involved in, say, automotive, grid energy storage, medical devices, etc. If you're designing any sort of lithium-ion system, you have to know these basics. System configuration, let's say you're doing field deployment of battery modules and strings. You want to know this stuff. Complex lead-acid systems requirements, or if there's any sort of lead-acid parallel strings, you want to know about this stuff. They're somewhat rare, but sometimes they do exist, lead-acid parallel strings. And then if you just want to do a basic review of a basic lead-acid series stack-up, review the basics. You can take a look at this stuff. Introduction. So we want to introduce you a little bit to systems thinking here. You got to get away from just thinking about the cell, and you got to think about the end user, the end requirements of the system. Because putting hundreds of cells together, or even a handful of cells together, is a system. You're no longer messing around with a particular cell. So you have to figure out how it works in a system. So whenever you're working from a system perspective, you want to always pay attention to the black box perspective of the system. So batteries, when you get down to what they do, is energy storage. And energy is a physics equation, right? So energy is basically power multiplied times a time interval. Power is, let's say, watts. I need 100 watts for 3 hours. All right, and you get your watt hour. So watt hours is your energy. You can review these physics equations in your high school physics book, perhaps. But anyway, so on the black box for series parallel stack-ups, you need to know your power and you need to know time. And these two, power and time, always give you energy if you do the calculations correctly. So remember the black box perspective on your system. Always remember the black box perspective. Forget about the batteries, forget about the voltage, forget about the current, and say, how much energy do I need? And then you backwards calculate your voltage, your current, your amp hours, and your etc. But you need to know your watt hours required, and then you back calculate how much voltage to stack up and how much current you need to get the amount of energy you're looking for. So never forget the black box perspective when you're designing battery systems. You just got to know how to think through it that way. So let's look at a single cell at this point right now. So the single cell is going to have a voltage. This one right here is 2 volts. It's going to have a charge in amp hours, 10 amp hours. It's just as a review, a Coulomb is an amp-second, so an amp hour is, you just use your multiplication factors. Energy is always going to be voltage times amp hours. So energy, voltage times amp hours for the cell calculations in the battery systems. That's for a single cell. So this one right here is a 10 amp hour cell at 2 volts. You multiply 10 times 2, you get 20. 20 for the energy, 20 watt hours. Okay? So let's take this cell and stack it up into a series system, all right? So this is the representation of a series system right here. So whenever you take a single cell and you stack it up into a very simple series system, the charge or amp hours do not change, all right? So you get the same amount of amp hours, 10 amp hours. The voltage increases to 4 volts from 2 volts. Because it's a doubling on a series stack. Your energy is always dependent upon the number of cells only. So every time you do your energy calculations, all you got to do is add up the number of cells in the complete system. So you take the energy of the individual cells and you just add it up. That gives you your energy for any sort of stack up. But the tripping point is the amp hours or the charge. So that does not follow the stack up for the cell. It's only follows the actually the parallel stack up. So again, in review, voltage goes up Energy goes up because you're adding another cell, okay? Current stays the same for a series stack up, a simple series stack up, and amp hours remains the same. So you get 10 amp hours for a series stack up, same as a single cell. So the amp hours does not go up for a series stack up, a simple series stack up. All right. Now, let's take this cell and do a simple parallel stack up and see what the numbers do here. See how the system gets configured. So we're going to take two cells, put them in parallel, okay? Now that you have better current capabilities at a parallel stack up, the amp hours increases. So your amp hours go up. Your voltage remains the same in a parallel stack up because this rail and this rail are at the same voltage. Your watt hours is always dependent upon the number of cells in any system again. So we have 20 watt hours for a single cell. For two cells, it's going to be 40 watt hours. Let's go again. The current capabilities go up because for parallel systems, you increase your current capabilities. Whereas for the series system, you do not increase your current capabilities. So the current capabilities go up in a parallel system. The voltage does not go up in a simple parallel stack up. The energy just goes up because there's an extra cell aside from the single cell, and your amp hours go up for a parallel stack up. So those are the basics for a very simple series stack up and a very simple parallel stack up. One note in series parallel stack ups that you must know if you get involved in lithium ion batteries or more complicated systems than single parallel sets up is the S and P encoding of the system. How do you talk about a battery system with a certain amount of series cells and a certain amount of parallel cells? Okay, so you take each cell in a system and the amount of series cells, you put the number of cells in front of the S, and the amount of parallel cells, you put the number in front of the P. So this system right here is a 2S 1P because it's two cells in series and one cell in parallel. This one, however, is a 1S 2P because you have two cells in parallel and one cell in series, one level in series. The weird thing about this that you need to keep in mind is that a single cell does have its own nomenclature also. The single cell is a 1S1P. This might sound weird the first time you hear it, but basically it's one cell in series, one cell in parallel. A single cell. And the way to think about it is it's one level series, one level parallel of a cell. So remember, a single cell is always going to be 1S1P. A very simple series system again is 2S1P, two in series, one in parallel. Very simple parallel setup is always 1S2P, one in series and two in parallel. So you need to learn this this way of coding up the number of cells in a stack up if you're going to do battery systems. So, all right, let's move on to the other whiteboard. All right, now let's look at the concept of a battery rail. So we're looking again on the system level here. So a battery rail is like looking at the top level of the system requirements for voltage, mostly, and or current. So what I did here was in this diagram here, I have this black line representation of the positive rail and this bottom black line representation of the negative rail. So I put a positive symbol there and a negative rail symbol here. And a battery rail is composed of several battery strings connected to the rail. You can think of a string as a literal string that you're holding like this and it hangs down from the top to the bottom. So you can think of a battery string as hanging from top to bottom, like one string, second string, and then the third string. So this is like three strings on a battery rail system. Let's look at a single string before we get into this. So let's take, for example, the same cells we had in the other whiteboard which is 10 amp hours at 2 volts at 20 watt hours. Okay, so let's stack up that cell to 300 in series. Okay, so we're gonna say use this representation of the 300S 1P system. All right, so if we have 300S 1P system, it's only one string in parallel, so we have the same amount of amp hours, 10 amp hours. However, the voltage is basically 2 volts times 300, which is 600 volts. The amount of watt hours is just basically adding up the energy of each cell, and that adds up to 300 cells times 20 watt hours, and that comes out to 6,000 watt hours for this string right here. All right, so this is going to be a basic string that we're going to drop onto a battery rail system in the configuration of a few strings. Okay, so again, 300S 1P, 10 amp hours for this string, 600 volts, and 6,000 watt hours of energy. So now we're going to take this string and we're going to put 3 of these strings onto a battery rail. Recall positive rail, negative rail. See, positive rail, negative rail. I'm going to take 3 of these strings and place it onto this rail. So you got string 1 here, string 2, and string 3. So how does that change the system? So now this system is a 300S 3P. All right. Single string is 1P. When I put 3 of them on the rail, it becomes 3P, 3 in parallel. All right. So now that we have 3 parallel systems, we have 30 amp hours. Remember, a single string is 10 amp hours. We have 600 volts because we still have the same amount of series stack up in these 3 strings, so we still have 600 volts. But now we have 18,000 watt hours. Remember, the single string is 6,000 watt hours times 3 for the 3 parallel strings on the rail becomes 18,000 watt hours. So now we've covered a good bit of territory here with a single cell. Then we stack that up into a series stack up. Then we take the single cell and put it into a parallel stack up. Then we stacked it up into a larger string stack up. And then we placed a few of these strings onto what we call a battery rail. All right, string inserted onto a battery rail, whereas you can increase your capacity, increase your charge, amp hours, and increase your range. So that covers a good bit of territory. If you have any questions, send me an email at the end of this lecture here. We'll try to answer your questions, and you guys stay safe out there. Take care. Till next time. Bye.